So what we've seen is that corresponding to each process, we have a process page table, right? So now let us try to understand what is the size of this page table, right? So if we assume a 32-bit system, then the virtual address space, as we've discussed earlier, ranges from 0 to 2 power 32 minus 1, and that corresponds to 4 gigabytes, right? Now, if the size of each page frame is 4 kilobytes, that corresponds to 2 power 12 bytes, right? So what it essentially means is that for each 2 power 12 bytes, we have a mapping, we have an entry that is present in the page table, right? So why is this here? Okay, yeah. So the number thus the number of entries in the page table is 2 power 20. So how do you get this? Because essentially we have a virtual address space of 2 power 32 divided by the size of each frame, which is 2 power 12, and therefore we have 2 power 20 entries in the page table. In other words, this particular page table is going to have 2 power 20 entries, right? Furthermore, if we make an assumption that each entry is of 4 bytes, that is means to say that each entry in this page table is 4 bytes. So essentially we require 4 megabytes of contiguous memory to essentially store the page table, right? While 4 megabytes is not a big value, big number, the problem is that this memory needs to be contiguous, right? And this can be an issue. If we actually have multiple processes executing in the system, in a multitask system, it may be difficult to find 4 megabytes of memory contiguously, which are contiguous and also which are free, in order to essentially store the entire page table. So what modern computer systems do is, in order to handle this issue, we make use of a multi-level page translation, right? So the virtual address does not directly go and index into a page table, but rather is divided into different components. So for example, in a 2-level page translation, in a memory management unit which supports 2-level page translation, you have a virtual address which is, say, of 32 bits, which is essentially split into 3 components: a directory component, a table, and an offset, right? So here, for instance, we have the directory component, which is the most significant 10 bits. Then you have a table component, which is or the table bits, which is another 10 bits, and finally you have an offset which is of 12 bits, right? So the directory bits are used to index into what is known as the page directory, right? So the page directory is a 4 kilobyte page. It is stored in the memory and essentially is pointed to by a register known as the page table base register, or PTBR, right? So the directory bits is essentially used to index into the PTBR into some particular location, right? So this entry in this page directory does not essentially directly point to a page frame which holds the process data, but points to an other level of page table, which is the second page table, right? And therefore this second page table can be indexed, right? So what this essentially means is that every entry in the page directory points to another layer of page tables, right? Each page table is of 4 kilobytes, and the table bits of your virtual address, that is the second set of 10 bits in your virtual address in this particular example, is used to index into the selected page table, right? Now from the selected page table, one can essentially read and other sets of bits, right? Or these bits are then concatenated with the offset to finally obtain the physical address. So what we see over here is that to convert the virtual address into the corresponding physical address, It's not just a single lookup into a page table that is needed, but in this example there will be two levels of lookups. The first level would essentially look into a page directory, find the offset of where the second level page table is obtained. Then we use the table bits to index into the second level page table. You obtain the entries over there, which essentially is the page frame number, right? Concatenate the page frame number with the offset bits, which is 12 bits, to form the complete physical address. So this physical address is now used in your DRAM to collect the data, right? So how does this essentially help, right? So if I just look at the size, we still require 2 power 10 pages, that is 1024, and the total size of the page tables is still 4 megabytes. So at first sight you may actually think that this is not very useful, because we had 4 megabytes earlier, but we still have required 4 megabytes to store the page tables. But the important difference is that in this case the 4 megabytes does not have to be contiguous, right? And this is much more easy for us, because we can find these 4 megabytes scattered across the RAM at various locations, and can be used as different page tables, different page table entries. The second advantage is the fact that if we have, let us say, a particular range of addresses that are not being utilized by the particular program, then we may not even require a page table for that. So for instance, we may essentially have let us say an entry in my page directory, and the program does not essentially at any time during its execution essentially make use of these addresses corresponding to this entry, right? In such a case, we may not even require such a page table. Okay, so so in other words, this 4 megabytes is the maximum amount of memory that is required, right? In most cases, the amount of memory to hold the page tables will be considerably lesser. The reason for this is we create these page tables, the second level page tables, on demand, right? So if only if there is an access to this particular to some address that is held by a particular page table, only then would the page table be created, right? If no such access is made, then you do not require the page table, right? So let us see the entire process, right? So what happens? So I am writing a program, I am having a statement something like this, say int x equal to say ampersand y, right? And I am doing star x or something, right? So I am trying to access a particular memory location, right? So in this case, I am trying to access 4 bytes, because integer is 4 bytes. So when I compile this particular program and execute it, the CPU essentially converts this star x into a load instruction from a particular address. Okay, this address is essentially a virtual address and would have the form like this, right? So the address that is emitted out of my CPU, if my CPU is here, the address essentially emitted out of my CPU is essentially this address, which is a virtual address. It would comprise of the directory bits, the table bits, and the offset bits. Okay, so the first thing done, so this virtual address goes into the memory management unit. The memory management unit knows the page table base register, so it uses the page table base register, which is a register present within the memory management unit. It uses the 10 bits of the directory entry to index into the page directory, right? And then identify the offset, index into the second level page directory, and use that to identify the page frame, append the offset to create the physical address, right? So let us see how this essentially works in a 32-bit RISC-V machine, right? So there are multiple components that are involved, and we look at each of these components. Okay. The first thing is this page table based register. So, this page table based register is a register in the memory management unit which is present within the processor. In RISC-V, this is called as the SATP register, right. So, it has 32 bits and is split into mode bits, ASID bits and physical page number bits or PPN bits, right. So, the mode bits essentially will tell you whether there is a page translation or not, right. So, if this mode bit which is essentially one bit, the 31st bit, whether if it is 0, it essentially means that there is no address translation to physical address. In other words, we are disabling the memory management unit. So, what it means is that any virtual address that is sent out from the CPU, the corresponding physical address is generated. So, every physical address is equal to the virtual address when the mode bit is set to 0. If the mode bit is set to 1, then it means that we have to go through this page level translation, convert the virtual address to the corresponding physical address, right. So, right. So, the next set of bits is the ASID bits, ASID. So, the ASID essentially stands for the address space identifier, right. So, these are 9 bits and in a multitask environment where we have multiple processes executing, this ASID bits is used to distinguish between one process and another, right. So, in other words, it is used to distinguish between one virtual address space of one process and another virtual address space. So, finally, we have the PPN bits, right. So, these are there are 22 such bits, the least significant bits, and the physical page number essentially is a pointer to the physical memory which holds the page directory, right. So, this pointer that we see over here from the page table based register, in this case the SATP register present within my memory management unit, is essentially pointing to one page frame which is of 4 kilobytes and holds the page directory, right, or in other words the first level of page tables, right. So, right, okay. The next thing is about the virtual addresses, right. So, the virtual address, as we mentioned, so this is a 32-bit system. The virtual address would be emitted out from the CPU when I do the something like the star X. So, this would correspond to a load and the address is essentially emitted out of the CPU and comprises of 3 parts. Unlike the standard nomenclature, RISC-V essentially calls this as offset, level 0 and level 1. Okay. The virtual address is essentially split like this. So, it is of 32 bits and it has this 10 bits for VPN 1, which is virtual page number. The second 10 bits is, so this first 10 bits is essentially the directory bits. The second 10 bits is essentially the page table bits or the page table bits. Yeah. And the final 12 bits are essentially the page offset. Okay. So, so the virtual addresses of this, the page table base register, the SATP register, is used to essentially select an entry in the page directory or the page table, and finally an entry in the page table is selected, right. So, page table entry, whether it is in the page directory or in the page table, has this particular format, right. So, this page table entry is very similar to what we have seen earlier, yeah, that is this, with a lot more information essentially present, right. So, the most critical part of this page table entry are the physical page numbers. So, that has a total of 22 bits. It has PPN 0, that is physical page number 0 and physical page number 1. Then you have the dirty bit, which we have actually mentioned, right. The dirty bit would be set to 1 if there has been a modification in that particular page frame, and the contents of the page frame needs to be written back into the hard disk when there is a swap out. If the dirty bit is set to 0, then this writing back to the hard disk is not required, because no changes, no modifications have been made to the page frame, and the contents are exactly identical to that present in the hard disk, right. So, the accessed bit A is essentially the equivalent to the P bit, right, the present bit which we have discussed earlier. So, if there is a page that is present and there is a mapping from the memory block to a corresponding page frame, then you have the accessed bit set to 1. Okay. Then we have the X, W and R. So, these are essentially the protection bits. Right. So, X essentially tells you whether that particular page frame can be executed, right. So, if you have a code section or a page frame that comprises of code, then it would have the X bit set to 1, right, meaning that the processor can actually execute the contents of that particular page. If you have the read bit set to 1, it essentially means that the page is readable. If you have the write bit set to 1, it essentially means the page is writable, right. The read essentially says that you can, because it is read, so essentially you can load from that particular page. So, the load instructions would actually work from that page. If the write bit is set to 1, then essentially it means you can store from that particular store to that particular page. So, the valid essentially indicates whether that particular entry is valid or not, right. So, if it is set to 0, it essentially means that the bit is invalid, or the entry is invalid. If it is set to 1, it essentially means the page, that particular entry is valid, right. In addition to this, the RISC-V page table entries have these 2 bits corresponding to a user bit and a global bit. So, user bit essentially indicates that the page corresponds to a user space or a user program, and the global bit essentially says that whether the bit is a global or local, right. If it is set to 1, essentially it would mean that the particular page frame is a global page frame. It is essentially shared, right, across multiple processes. Okay. So, the last thing that we need to look at, so every entry in the page directory and the subsequent page tables and so on have this particular format. Finally, we have this physical address, right. The physical address has bits from 0 to 33, right. So, it has the 12 bits for the PPN, that is a physical page number, a second 12 bits for the PPN again. So, it is total of 10 plus 12, so 22 bits for the page frame, and you have a page offset which is of 12 bits. So, very similar to what we have seen earlier. Okay. So, we will go the XP6 operating system that we are essentially studying. Suppose the RISC-V 64 works on a okay. The XP6 OS which we are studying as part of this course essentially works on the RISC-V 64-bit platform, right. And therefore, we will also look at how the memory mapping or the memory management takes place for the 64-bit platform as well in RISC-V. So, RISC-V 64-bit essentially supports 2 modes of operation. It supports a 39-bit and a 48-bit mode of addressing, right. Now, the SAT-P register for the 64-bit RISC-V looks something like this, right. So, it has 64 bits, of which 4 bits essentially tell you the mode, 16 bits tells you the ACID value, that is the address space identifier, and then the 44 bits essentially tell you the physical page number. Okay. So, the SAT-P register, the mode of the SAT-P register tells you whether you're doing 39-bit addressing or the 48-bit addressing, right. So, if it is set to a value of 8, 8 is essentially 1000, it means that your processor is operating with addresses of 39 bits. Right. If your mode is set to 9, it means that your processor is operating with a 48-bit addressing, right. So, when a virtual address is sent from the CPU to the memory management unit, the SATP register in the memory management unit is going to be used to identify whether this address is a 39-bit address or a 48-bit address. Okay. Accordingly, the mapping from the virtual to physical address essentially is done. So, in RISC-V, in the x86 platform, we use the 39-bit addressing, right. And just to recall very quickly that we've been looking at the x86 code, specifically if I go to the kernel and I look at this file called riscv.h, I can just go to line number 185. So here is where we essentially define the SATP, right. So you see that we are having an hash define SATP underscore SV39 8L left shifted by 60. So what are we trying to do over here is that we are trying to set the mode bits, right, eventually set the mode bits of the SATP register to a value of 8, which means that we are trying to set a 39-bit addressing, right. And we also have this macro called make SATP, right. So which takes this input called page table and essentially it sets or it creates this page table where the SATP value, the most significant 4 bits of the SATP value would have the value of 8. Okay. So these are your hash defines, and let's see where they are used. So we can find out where these are essentially used. So I can just grep for SATP SV39, right. So yeah. Where is it used? Make SATP. Yeah. So yeah, so this particular macro, so if you actually see here, right, so this function kvm init heart is invoked from the main, right, and we'll actually come to this later on, where we invoke this function w underscore SATP make SATP kernel underscore page table. So what are we trying to do over here is that we are trying to set the value of the SATP register within the processor and set it to essentially 39-bit addressing, and also set the lower bits, the 44 lower bits of the physical page number in the SATP register to point to this kernel page table. So this is where you would have the page directory for your page table. Okay. So we'll get into the code a little more in detail a bit later on, but for now, with this 39-bit addressing, let us see essentially how the 39-bit addressing gets translated into a physical address, right. So unlike the 2-level page translation that we have studied early on, with the 39-bit addressing in RISC-V, it essentially supports 3 levels of page tables and can support not just 4 kilobytes but also support 2 megabytes and also 1 gigabyte pages. The virtual address in the 39-bit addressing mode comprises of 4 components. Bits 0 to 11 are the page offset, which is kind of similar to earlier, but we have the 3 levels of virtual page numbers, the VPN 0, VPN 1 and VPN 2. Okay. So notice that this is only 39 bits, right. So if you have an address which is of 64 bits, the remaining bits from bit 39 to bit 63 would be set to 0. Okay. The second thing you would notice is that we have because we have 3 levels of page tables, the page directory, first level page table, second level page table. Then each entry, each page table entry has 9 bits. So we have a total of 2 power 27 page table entries that are present. Okay. So this is how the virtual address would look like. You have offset, which is 12 bits, L0, level 0, level 1 and level 2, which is of 9 bits each. So the first thing is that when this virtual address gets generated, it goes into the memory management unit. The SATP register is used to point to this level 2 page tables, which is essentially a page directory, and the topmost significant L2 bits is used into the offset. Then you have the second level of page tables, which is the L1 page tables, which gets indexed based on the entry present here in the L2 page table. So you identify first one level 1 page table, and then you index into that, and then you have a third page table, and finally from the L0 page table is what you get, this 44 bits of the page frame, right. So the 12 bits of offset gets added on, so you have 44 plus 12, which is a 56-bit physical page address. So what this means is that at the maximum you can have 2 power 56 possible bytes of addressable physical memory that can be present in your system, right. So for every virtual address that gets created, this 39 bits of virtual address gets converted to a physical 56-bit of physical address, right. Yeah, okay. So again, going into a little bit into how XP6 uses this and what the page table entry looks like. We see that a page table entry looks like this. It has 64 bits. It has PPN2, PPN1 and PPN0 corresponding to the different physical page numbers. So each is of 26, 9 bits and 9 bits. So totally there are 44 bits, right. So notice that we have the page frame number is of 44 bits. Okay, and then we have the various flags, the dirty, accessed, global, user, execute, write, read and valid bits. So this 64-bit entry is what forms your page table entry in your 3 levels, in each of the page tables present in the 3 levels. Okay. Now these page table entries needs to be configured by the operating system. So we've already seen that the operating system has some macros to configure the SATP register. In a very similar way, we would also see that the operating system has some code to configure the page table entry, right. In XV6, again in the RISCV.h file, you have this particular macro called PA to PTE, which is essentially the page table entry for a physical address, and this macro, if you would actually see, so it takes a physical address, left shifts it by 12 bits to get rid of the offset. It takes the physical it takes the physical address, which is of 64 bits, right shifts it by 12 bits to get rid of the offset, and then left shifts it by 10 bits, right. So left shifting by 10 bits essentially brings that physical address to this part where you have this PPN0, PPN1 and PPN2, and now this PA, right, PA to PTE can be used into this region of your page table entry, right. In addition to this, the page table number, we also have the various flags defined, like the valid flag, which is at an offset of 0 bits. We have the read, write, execute flags, which are offsets of 1, 2, 3 bits from the least significant bit, and we have the user bit, which is an access of 4, offset of 4, right. So what we can see is that with these macros defined in RISCV.h, we can essentially create a page table entry, right. And as we progress, we look at the code where the OS essentially creates or uses these macros to create page table entries. So you could also look into your RISC-V code and essentially see how these macros are utilized, right. Okay. So yeah, the physical address is quite simple. We have 44 bits of physical page numbers, that is PPN0, PPN1 and PPN2, plus the 12 bits of a page offset. So this is fairly simple, right. So let us take the small code. So x equal to y and y equal to y plus 1, right, and see the process and of what happens in each instruction, and essentially let's essentially trace what happens, right. So first of all, what we see over here is that we want to be able to load some memory from the physical memory, of course, into this register X, right. And therefore this physical this Y, which is present in the physical address, the CPU would need to load it into a register X, right. And for this, you create it would create a virtual address corresponding to the address of Y, and load that emit this particular virtual address on the address lines, right. The memory management unit would then use the SATP pointer to identify the top level page directory, or the L2 page table in this case, use the top 9 bits to index into an offset into this particular page table. Now this page table would have a 44-bit pointer to a second level page table, which is here. This is the level 1 page table, and there's a similarly the second 9 bits, or the L1 bits, indexes into it, identifies a third a pointer to the third level page table, which eventually has 44-bit page frame number. Append the 12 bits offset, and you would actually get the physical address. Okay, so notice that there are 3 components which are utilized in this, right. The orange is what is happening in the CPU. The CPU is essentially emitting this address of 39 bits. The SATP is used to convert that, or to the SATP is essentially present in the memory management unit, or also called the paging unit, and then the various page tables are essentially present in the physical memory, right. So to make one access and load a data from the physical memory into a register, you would essentially require a total of 4 physical memory accesses. The first is to the level 2 page table, second is to the level 1 page table, third is to the level 0 page table, and finally you load the address. You have generated the physical address. Now you load the corresponding data from the DRAM into the register, right. So this is a huge overhead, because every time you want to load something from memory, you are actually requiring 4 accesses to the memory, right. And the memory is considerably slower than the CPU, and therefore you are going to have a huge performance hit, right. So for example, so what is done in practice is that this lookups into these multiple level page tables is essentially cached in what is called as the TLB. So TLB is essentially a translation look aside buffer. So it's a cache memory. So and would be present in the paging unit, right. So what this caches is essentially the mapping from the top 27 bits of the virtual address to the corresponding 44 bits of the page frame number corresponding to the physical address, right. So, so when an entry is essentially done like this, right, like you traverse through the multiple page tables, create the physical page number and the physical address. So, internally within the page tables corresponding to the L0, L1 and L2 bits, an entry is created in the TLB, right. So, subsequently if I happen to access another variable which is in the same page, for example y equal to y plus 1, right. So, we do not need to traverse through all of the multiple page tables again, or and therefore, you do not need to make 4 accesses. So, the virtual address which is again in this which is almost similar because you are accessing the same address in this case. So, 27 bit virtual address, you would just look up the cache present in the memory management unit, the paging unit, and directly obtain the 44 bits of page frame number, right. And therefore, if therefore this access, right, the second access to this to the same pages or the pages which are already been loaded would be considerably faster, right. So, as long as I have a large enough TLB cache, I can cache quite a bit of virtual to physical mappings and eliminate a lot of page table lookups,